here's problem number 49 from section 9.4. It's a telescoping series, and the telescoping series share this attribute. We first attack it by looking at partial fraction decomp, and then we start looking at the partial sums until we get a feeling for what's going on, and then we look at the limit of the nth partial sum as n goes to infinity. But first things first, let's do a partial fraction decomp. 6 over 2n minus 1 times 2n plus 1 can be rewritten as a fraction where a is over 2n minus 1 and b is over 2n plus 1.
Yes.
Solving for it with a common denominator, we end up getting that 6 is equal to a times 2n plus 1 plus b times 2n minus 1. Now, since this is true for all x, why don't we choose an x that's convenient for us? Why don't we try x is equal to negative 1/2?
Do you mean n?
N is negative 1/2. There we go. So when n is negative 1/2, the multiplier on a becomes 0, and we simply get 6 is equal to b times negative 1 minus 1.
Yeah.
Double check that.
B is negative 3.
So b is negative 3. When we force n, as an x that turned into an n, to be 1/2, then the b stuff goes away, and we're left with 6 is equal to a times 1 plus 1, or that means that a must end up being 3. So this partial fraction decomp becomes 3 over 2n minus 1 minus 3 over 2n plus 1.
Is that like the battery series?
No, don't think of it that way.
Oh, compound.
Because it's got. First of all, I want you to know this is going to converge, and you already know that by inspection,
P series test.
because it nets out to a p series of p equal 2. It looks like it compares to 1 over n squared. You already know this converges, all right? So here's what's left for us to do. Let's talk about the first partial sum. What happens when we start trying to add up the values of this series? Well, when n is 1, we end up with 3 over 1 times 2 is 2. Sorry, is 2. 2 minus 1 is 1. So I end up with a 3 there. Minus 3 over, when n is 1, 2 plus 1 is 3. Okay, now that's not enough to get you full insight. So let's look at the second partial sum. What if we added the first and the second terms together? Well, we get the 3 over 1 minus 3 over 3 from the first term plus 3 over 3 minus, and I believe this ends up being 3 over 5 from that second part of the second term. Then we go to our red pen, and we notice that those terms cancel. Let's go look at the third partial sum. We've got the 3 over 1 from that first. We don't rewrite the stuff that canceled out, but now we have a 3/5. But now I have to add the third term.
Plus 3/5.
Plus 3/5 minus 3/7. Again, that's taking this expression and plugging in any, 3 for n. Oh, look at that. Those go away. If we've seen enough, perhaps we get to the point where we can say, well, what is the nth partial sum? 3 over 1, and then there's going to be some minus, and it's going to be 3 over 2n plus 1.
So as n approaches infinity, the sum becomes...
So the value of the infinite sum is the limit as n approaches infinity of the nth partial sum, which is, in this case, the limit as n approaches infinity of 3 minus 3 over 2n plus 1. The 2 plus 1 is in the bottom. It goes to, as it goes to infinity, that fraction goes to 0, leaving us nothing but 3. So not only does it converge, but with telescoping series and geometric series, we can actually find out what it converges to. Yes, Austin?
Can you also do the integral test once we find out the decount?
Okay, that's a really good question. Could we do an integral test on this? Well, the integral test will tell us whether it converges or not. But we already knew by inspection that it converged. Yeah. If we did do the integral test, it does lead to some interesting insights about the nature of the error if we use the partial sum. But besides that, there's not much there for the integral test. We already know that it converges. All right. That was for you.
Thank you, Mr. Fedor. You're such a kind person.
All right. Well,
Where's your shirt translate?